So my talk today will be about measuring inconsistency in evidence theory. Yesterday, there are a couple of questions regarding Thierry's talk on the least commitment principle. And it says it's a kind of qualitative approach to compare two mass functions to belief functions. So this talk is rather about on the quantitative side, how to quantify information content. So this talk is about these two aspects. What I call the inconsistency measure can be split into two aspects. Unary measure, measuring the internal inconsistency of a belief function that are typically extending Shannon entropy or based on a definition of consistency. And on the other hand, binary measures that are external measures of inconsistency, which quantify how two mass functions, two belief functions are different, inconsistent, distant, and typically measures of conflict or distances, such as the one Thierry mentioned in his talk again, and Frédéric as well yesterday. So the purpose of this talk is not to talk about all these kinds of measures, but to survey internal and external measure of inconsistency with a specific focus on the generalization of these measures, how we can make them a kind of general formulation and establish links together. So that will be the outline of my talk, quite simple, some preamble to define the basic notions. A first part on unary measures or internal inconsistency measure or uncertainty measures, binary measure, or external inconsistency, a few words on some applications, and then conclusions, which will be rather a summary than conclusions because a lot of work remains to be done. So let's start from some notation. Everything's just to set up the notations I will use in this talk. So I will denotate by big X the frame of discernment, its power set. I will use little x for denoting an element and so on. The important aspect, the cardinality of a set, the complement of a set, the intersection, which will be quite used in this presentation. A mass function is M. This set F will be the set of all focal sets. So the set of all sets that have a positive mass function, a positive mass, sorry, and Bell, the belief function and the plausibility function. So some reminders of what you previously saw. M is said to be normalized if the mass of the empty set is 0. It's Bayesian if all focal sets are singletons. It defines a probability distribution. It's logical or categorical, depends the same, it's a synonymous. If the mass function has a single focal set, and it's equivalent to defining a classical set. And I would like to emphasize two important categorical mass function, the one where all the mass is assigned to the frame of discernment and represents total ignorance, and the one where all the mass is assigned to the empty sets, which represent a state of total inconsistency. So some basic measures in both probability and classical sets. So first, I want to highlight what has been said many times, but that belief functions extend both classical sets and probabilities. So in the end, what we have is rather a distribution, a kind of probability distribution on a series of sets with the, with the specific thing is that the mass of the empty set can be also assigned some value. So here, this is the empty set in the middle. So naturally, when we define some basic measures, we have to consider both what has done in the classical set theory, what has been done in the probability theory. So some basic measures of uncertainty information, depending on how you think about them. In classical set theory, the basic measure of information or uncertainty, if you prefer, is Hartley entropy, which is simply the logarithm of the cardinality of A, and it's equal to 0 once you have no imprecision, no specificity. And in probability theory, the basic measure of uncertainty is Shannon entropy, which is 0 if the probability of a singleton is equal to 1, and it's maximum for a uniform distribution, so it's maximum uncertainty. On the other hand, on basic measures for when you compare two functions between sets, an example of a distance between set is this one, which is 1 minus the Jacquard index here, and it defines a full distance between set. It's one example among many other, but just to say that there are ways of measuring distances between sets. We can measure also the Euclidean distance between probabilities, which is a classical definition of distance. And we can also, in probability standard, to measure some divergences, like the Kullback-Leibler divergences, to compare also two probability distributions. So the question is, how do these things articulate when it comes to measuring uncertainty, distances, conflict within belief function framework? So I will try to highlight in this talk that the notion of consistency can be seen as a central concept for a lot of measures. Maybe not all of them, but a lot of measures. So we say that two sets are consistent if their intersection is not empty. So that's nothing really complicated and no real strict constraints. And we can define a consistency index to satisfy minimally these two constraints. It's 1 if the two sets are equal, and it's 0 if the sets are empty. And we can define a series of consistency indexes, all of these, that I will go a little bit in detail. So we have one way of saying that two sets are inconsistent, do not intersect, while there are several ways that set intersects in general case, but it's also the case when one is included into another and when they are equal. And if we refine a little bit further, we can also consider the elements within the set. So we don't go from a binary index 0, 1 to something which is more a quantitative notion of what I would say consistency, because all of these indexes are still 0 once the sets do not intersect. So what we can see easily is that all the uncertainty functions that have been defined so far can be put under this form, where appear here the consistency index between two sets. So it's an expectation over all the focal sets of a consistency index relatively to a particular set here. Here we see that we can write that way the plausibility function, the belief function, the commonality, and the mass function with specific indexes, but also the pygnistic probability and other functions that have not been defined for over series of sets. Not saying that they are meaningful, but that's possible to define. Not saying that it's interesting to do them, but that's still just the general formulation. So let's start with the first part on Unary measure, measuring internal inconsistency, internal uncertainty of a belief function. So again here, so first of all, let's go back a little bit. There are several types of uncertainty in general that have been categorized that way by Clare and Young. So you have fuzziness and ambiguity. Ambiguity itself is what is captured by evidence theory in general. So ambiguity can be split into non-specificity, which is related to the cardinality of the focal sets of the belief function, and discord, which is rather related to the way to the distribution of the masses on the focal sets. And it can be seen as also, these are synonymous of dissonance, incongruity, discrepancy, conflict. So this aspect will be actually the focus of my talk. I will talk very briefly of these two general measures, but it's not the focus of my talk. So let's start with a brief survey. As I said, this is the basic entropy-like measures. The aim of the authors at that time, and these references are quite old at the beginning of the basic functions in the 80s, mostly. The intent was to extend Shannon entropy. So a series of measures have been defined here, which can be put under this general form. They all generate to Shannon entropy and Hartley entropy when the belief function reduces either to a probability distribution or to a classical set. So they are all zero if for a maximal consistency where there's a single focal set which has a mass function of 1. Another approach which has been followed is starting with a definition of consistency first. And these are the measures that have been defined. So this is in particular, and one interesting is the consistency that has been defined by Ron Yeager. Actually, this sign here means that it didn't define the corresponding inconsistency, but he focused on the consistency itself, defining this function, which is the expectation of the mass multiplied by the possibility, and I will come back later on this meaning. These two authors defined a notion of total conflict, where here it's a double expectation, weighting the distance between two sets using Jacquard index here. A logical inconsistency, which the name is rather due to the author here, which is 1 minus the plausibility of the singleton, or simply the mass of the empty set, as we said earlier, which turns to be 1 minus the maximum of the plausibility over all the focal sets. So this measure all satisfy this general formulation is 1 minus an inconsistency measure that I will denote in the talk. So I will keep this notation delta for inconsistency, conflict distance, and etc., which is the negative or how uncertain distance measures are, and phi, which is rather the opposite, which is consistency or similarity and so on. So they do not extend Shannon and Hartley entropy. The authors rather focus on the inconsistency between sets. So they are all zero if all focal sets intersect. So it's rather the dual notion, rather focusing on the set notions weighted by the different mass functions, by the different masses, or focusing on the distribution for entropy measures. So the question is, can we establish links between these measures? So we have two quite general formulations, and I will try to show examples of a couple of results, how we can do that in two steps. So first, by defining what is the total consistency of a mass function, and then defining what is the total inconsistency of a mass function. So how to group them together? First, I will present the notion of inconsistency, some properties, definition, and then the measures. So what does it mean for a mass function to be consistent, and what a measure of consistency for a mass function must satisfy? We say that the consistency measure should satisfy the following properties to be bounded, usually between 0 and 1, but not necessary. And what is the main or the minimal condition that we can put for this measure is about the extreme values. So we want this function to be minimum is if M is totally inconsistent. There's a single definition of total inconsistency, which is when all the mass is assigned to the empty set. And we want it to be maximum when M is totally consistent. And here, there are many definitions of what it means to be totally consistent. And in particular, in the literature, there's the definition of probabilistic consistency. I will show you the definition. I mean, we showed it in the previous slide, of pairwise consistency and of logical consistency. So by observing a little bit how these measures of probabilistic consistency, pairwise consistency, or the definitions, let's say, of them, we can define a more general notion, what we call N-consistency, and we say that a mass function is N-consistent for N being a number of focal sets, if the interaction of any pair of any subset of N focal sets is not empty. So the one consistency coincides with the probabilistic consistency, and it is that all the sets, all the focal sets are not empty. But the pairwise consistency corresponds to the two consistency, meaning that you take any pair of focal set, their intersection is not empty. And the logical consistency corresponds to the cardinal F consistency, which is the maximum number of focal sets, meaning you take all the focal sets and their intersection is not empty. So based on this, we can define a family of measure of consistency that we call the N-consistency measure. And we say that is defined that way, phi n, where the parameter n, which is the number of focal set we consider, is 1 minus m power n of the empty set. This function here has been called, for instance, the autoconflict, is the combination of the mass function with itself n times, where we assume that the initial one is the vacuous mass function and it doesn't change anything in the result. So that means that it's just for calculation purposes, it's like an investigation of what is inside the mass function. So you combine it itself, with itself n times, and you obtain an empty set gives a notion of an inconsistency measure. So these measures satisfy the two properties depending on the definition of inconsistency that I showed you earlier. And this family is ordered, which is an interesting property, having at least these two measures defined in the literature, as this is the lower bound. And this measure is an alternative of a logical consistency to this measure. So this measure is called the logical consistency. It's a very interesting one, which is the maximum of the plausibility of the singleton, the maximum of the contour function. So just an example to show how it works. So this is an example for predicting the destinations of vessel. So here it's the coast of Italy, Corsica. We would like to know where the vessels are going based on a series of sources of information, meaning the information that has been sent by their IS, which is the transponder on board the ships, the routes, the maritime routes they follow. If they follow a specific route, they are more likely to go in different ports, and also based on the port visit based on their type and flag. An Italian vessel is more likely to go to an Italian city than others, and so on. So we have two mass functions like these ones, and the question is which among M2 and M3 is more consistent. So if we compute the N-consistency measure I showed you, we obtain this series of measures for n equal 1, 2, and the number of focal sets in the end. So here it's 3. And here the logical consistency. So we obtain a series of measures. And what is interesting is that two things. First is that with the classical definition existing, so which is phi 1 and phi p, we cannot discriminate these two mass functions based on their consistency. So they are equally consistent according to this definition. By refining and considering the notion of inconsistency, and just by the pairwise comparison of the focal set, we can actually discriminate and conclude that in this case, M2 is more consistent than M3. Then there's still another question. So for the discrimination is this part, we are able to refine the measures existing and allow some discrimination, which was not possible. But the problem is that this quantity here it seems that this measure, which is really important one, and that we cannot, I mean, we need to consider this measure. It's a really good measure that has all the necessary property for consistency measure and that are defined in the literature, doesn't seem to belong to this family. So to solve this problem, we defined another measure, which is called monotonic inconsistency measure, where we simply added, we simply take the n root of the previous measure. We obtain another family of measure, which is still ordered, with now what we can prove is that the upper bound is the logical consistency measure. So now we have that the family, the logical consistency belongs to this family. So it still satisfies the same property. This measure, this new measure, is also an alternative satisfying the logical consistency properties. So back to our example. So this is the result of the first, with the first measure here. By adding this n root, we obtain now an ordered family of measures, unordered measures, and this one is indeed the lower bound. So now, so this is first how we can make a general formulation for the measures based on consistency. What about now, can we connect to the way the entropy measures are defined? So to do this, we first extend the binary indexes to n-ary indexes. So this is an index between sets, which is 1 only if all sets are equal, and 0. So it's the same than defined before. So for instance, if we take this particular index, which corresponds, which is the one which is used in the case of n equal 2 for the defining the plausibility, we get that this index is equal to 1 if all sets intersect and 0 otherwise. So for mass function, so the question, the idea of this set is, as I said, to go from no comparison of focal set, just considering the focal set and they're possibly empty, to a binary comparison of focal sets, to an n-ary comparison of focal sets. So for Bayesian mass function, n-ary comparison, reduced to pairwise comparison, it's useless, but it's not true in the general case. And in particular, we can define now a consistency of one set relatively to the mass function. So we have a mass function, we consider one set, and we provide this general definition. So comparing, so you have, it's a sum of the sum of the sum of the sum for all focal set, except or including A as well, of this n-ary index that I just defined. So what is interesting with this formulation is that for one set, we get this simple index, which is a consistency index for one set, which is 1 if the set is not empty and 0 if the set is empty. It just tells if a set is consistent or not. For n equals 2, comparing two sets, we get the general uncertainty functions that have been defined earlier. So we can define the total consistency measure by this formula by taking the average over the local consistency of A. That's the way most all the measures are done. The entropy measures also is a kind of expectation over all the mass functions, over all the masses. And we can come to the general formulation of an inconsistency measure, an internal inconsistency measure. So we can write the total inconsistency of a mass function using this formula, where here there's the local consistency of a set relatively to the mass function, which is reversed here by a function. It's a classical function, which is a power function, which is interesting because we have a parameter here that connects with the logarithm minus the logarithm for A equals 1 or 1 minus x for a equals 2. So basically, we compute the local consistency, reverse it, and make the average. A controls the decrease of the inconsistency function, and N controls how many sets are compared for measuring the consistency. So by doing this, on all the measures that I presented you earlier, this reduces to only 3 parameters, A, N, and phi. And this is just an example to show, I mean, it's not really a table that needs to be, where all the boxes need to be filled. It's just to show how the measures are connected. So for A equals 1, we get minus the logarithm, and we get all here, all the measures of uncertainty, like extending Shannon entropy for N equals 2, because it's a binary, it's a pairwise comparison of focal sets. We get the measure of inconsistency defined by Jaeger. The logarithm does not exist, but the reverse function is 1 minus. We get George and Pal total conflict measure. But we get also here, for n equal 1 set, the mass of the empty set. And we get also here the n inconsistency. So that basically gives you an overview of the different unary measures defined for measuring the total inconsistency of a mass function. Not saying that everything is here, but most of it is here, which is not exactly finished, because I want to say a word about non-specificity and total uncertainty. Intrinsically, belief function can measure the 2 types of uncertainty, as I told you. So I want just to say some word about non-specificity and what Claire called ambiguity. So for measuring non-specificity, the debate has been closed quite early. This measure, defined by Dubois and Prad in 1985, is the only measure of non-specificity in evidence theory. It has been proved to satisfy and to be the unique measure satisfying the property of additivity, subadditivity, continuity, branching, normalization, and monotonicity. And I refer you to the literature to see both the proof and the definition of this, but there's no real discussion about how to measure non-specificity in evidence theory if you want to be compatible with classical sets. For total uncertainty, we can see 2 main trends. One that have been based on probabilistic transformation. So one idea is to first transform the mass function into a probability distribution and then take the Shannon entropy of this probability distribution. Another approach, which is not incompatible, which is a weighted sum by aggregating a weighted aggregation of first a non-specificity, the non-specificity measure, which is this one, and a measure which is either a measure of inconsistency that I presented you earlier, or one which can be seen as already capturing both aspects of uncertainty. So this measure is delta here is either a measure of total inconsistency or of internal inconsistency or total uncertainty, like this one. In particular, I refer you to a recent paper by Prakash, who follows this pattern and combining a probability transformation of the Shannon entropy with the non-specificity. Other formulation exists. It's not a full exhaustive survey, but at least I think you will have the basic references to pursue and to continue your exploration in this aspect. So I will continue now with the binary measures, so external, what I will call external inconsistency. So in this case, for when we want to compare 2 mass functions, 2 belief functions, classically the main categories of measures of conflict, measures of distances, but also other notions that can be also transferred to the field to belief functions like angle, cross entropy, divergence. I won't talk a lot about this, but mostly try to characterize these two categories of measures. So let's start first with measures of conflict, and going back to what to some definition, what does it mean to be totally in conflict? So we say that two mass functions are totally conflicting if the intersection of their core is empty. And the core of a mass function is the disjunction of all the focal sets. So that means that the two mass functions that are totally conflicting are no singleton, no element of the frame in common in whatever focal set you consider. So again, similarly to the notion of internal consistency, different definitions characterize the state of non-conflict. So we will denote that MF12, which is the set of all pairwise comparison of focal set, one for M1 and one for M2. So you take your two mass function, compute all the possible intersection of focal set of one of each mass function, as you do for combining in Dempster's rule. So we have a couple of definitions. One, non-conflict. I don't go back to the one, which is the same N that I introduced earlier. They are to say one conflicting if all the sets, all the intersections are non-empty. So this is basically when you compute Dempster's rule. If the mass of the empty set is empty, you can say that they are one non-conflicting. But you can go a little bit deeper. And you can also consider all the pairwise comparison of the resulting offset. If you take any pair of resulting subset after combination and their intersection is not empty, then this function will be said to be two non-conflicting. And the same until you take all the intersection of all the resulting focal set after the conjunctive combination. So the inconsistency-based measure of conflict, or would say that the conflict between two mass functions, can be defined as the inconsistency of their conjunctive combination. So literally, when we write this, conjunctive combination, consistency, inconsistency by reversing by 1 minus. So to each consistency measure previously defined, all the inconsistency, corresponds a conflict measure. And in particular, we retrieve for different values of n, Dempster's conflict, which is only this equation, and the logical conflict, which is 1 minus the plausibility of the singleton resulting after the combination. So if we consider the inconsistency, so the measures existing, we can redefine the notion of conflict that way. By here, we have the consistency measure reversed by 1 minus. That defines a monotonically ordered family of conflict measure with the property where this conflict measure, which is 1 minus the plausibility of the contour function resulting from the conjunctive combination, is the extremum, an extremum, and encompasses the existing measures of probabilistic and logical conflict, and they all satisfy the desirable properties considering the different notions of non-conflict. So that summarizes basically what can be done in terms of measures of conflict. Again, it's not exhaustive, there are other ways, but at least it encompasses most of the different approaches, or at least the most used so far. Now, what about distances? So let's say first a few words about the distance. So the notion of distance is quite intuitive. And let's see how it works for, again, the same example of a vessel destination. We have, in this case, three mass function. And the question is, we have a reference mass function, which is this one. And we want to know which of these two, M1 and M2, is closer to M star. So first, if we observe these two functions, because we see that this focal set is included in this focal set, while there's no link at all with this main focal set of M2, we expect that the distance from M star to M1 is lower than the distance from M star to M2. So, but because we do not share any focal set, if we take a classical Euclidean distance, then we will get exactly the same value, because it's just weighting the masses here, not considering the focal set. So obviously, we have to consider the consistency between focal sets to define a distance measure. Going back to the notion of consistency, I said that the notion of consistency can be seen as central to the definition of several measures. So the mostly known family of measures, which is the Minkowski family, you can define the Minkowski family of norm L alpha for a belief function by using this formula. So this F is the uncertainty function that I defined earlier. If you replace within this formula, then you make appearing here a consistency index between two sets. By different values of alpha, we get the different different measures, the different Minkowski norm, L equals 1, L equals 2. L equals 2, we got the Euclidean norm, which general formulation is this one, where we see appearing a pair of binary indexes comparing two sets. And we get the Jacquard norm, where we can make this index appearing here by a suitable definition of this index here. We get for L infinite, the Chebyshev norm, which is just taking the maximum of this function. And in particular, for a suitable definition of this index here, which defines the plausibility, actually, we get the maximum of the plausibility. What is interesting is that we have two means through the definition of a norm. It corresponds to actually the measure of consistency that I defined earlier. So the one consistency measure actually coincides with Chebyshev norm for the plausibility measure, but there are other examples as well. So Minkowski distance is simply defined by the norm of the difference between the two mass functions, and it can be defined that way. That can be right in a vector matrix form if you're interested, and if it's more natural for you to talk about distances with a vector form. So phi is a matrix of binary indexes, M is the corresponding vector mass defined on the power set. And here they are the main distances. So we can make varying the index between the two sets, varying the alpha parameter, and define a series of measures. So these measures have all been defined at different instants in time in the literature, and the main ones are these ones that I mentioned here. So first, the Euclidean distance between plausibility functions, which turns to be equal to the distance between the belief value. So there's no difference between both, simply because you make an average, and because of the duality relationship between the plausibility and the belief, which is 1 minus the belief of the complement, because in the end you sum up over all the focal sets, you will get exactly the same distance. So computing the distance between plausibilities and belief is the same thing. The distance between pygnistic probabilities, I think Frédéric talked about that yesterday. Maybe Thierry as well, I'm not sure, but Frédéric did. And also taking the maximum of the plausibilities, a measure that has been also quite used, or the maximum of Is there a minus here? Yeah, okay. So the maximum of the contour function. We can define the Jacquard distance by using this inner product. So this is the norm of M1 plus the norm of F2 minus the inner product of two mass functions, where here actually it's weighted based on the similarity between sets. This distance and also this distance between plausibilities are full metrics, meaning I will come back later to the meaning they are not pseudo metrics. So this is an important property in some applications. In others, it's not a property which is required. There are other distances, just to mention, just to open another family, Ellinger distance family that can be defined under this form, making up a ring still via a consistency index. Oh, sorry, the reference is question mark. An information-based distance family used, for instance, also by Thierry by defining, and it's interesting because it comes back to, it's basically the difference between the internal inconsistency of one function and the other one. So it can be quite useful in some application as well. And other functions based on interval, on the Wasserstein distance, and also recent measure defined by Arnaud Martin on distance on order set. I don't know if it can be useful for the discussion, but these kind of distances exist for the discussion you mentioned yesterday. So we'll conclude on this kind of survey on other types of measures, we will call inner product or cross-entropy. So if you remember the general formulation for n in general, but here for n equals 2, we can use two different mass functions here, actually, one here and one here. And that allows you to define the notion of cross-entropy, inner product, and that's this is a kind of measure that I think corresponds to the plausibility, the multiplication of the two plausibility will correspond of this family of measure. In particular for A equals 2, which corresponds to 1 minus the function, we get this measure, and we retrieve Dempster's conflict, 1 minus the inner Jacquard product, and a measure of cosinus, unnormalized, that was defined earlier. Now, the question is conflict or distance. You have two different, let's say, family of measures, two ways of quantifying how two belief functions, two mass functions are different. And the question is, what is actually the meaning of the different measures? So there's an intuition of what is a conflict, what is a distance, but still. So first, I would like to highlight the links between the two measures. So they are different, but we can establish some links. So if we go back to the monotonic inconsistency measure, which was defined by this formula, and the definition of the state of inconsistency, which is one for only for the empty set, we can define, so by definition of a norm, it's we can show that it's the consistency of a mass function is equal to the distance to the inconsistent state. It works for the plausibility measure, which is equal also to this norm here, but it works also for the contour function as well. So if we extend, so the consistency of a mass function can be seen at its distance to the total inconsistent state of knowledge. And if we extend to the definition of conflict, which is based on the notion of internal consistency, we can say that the conflict between M1 and M2 amounts to 1 minus the distance between their combination and the total inconsistent state of knowledge. So there's a mean to establish, so these are Dempster's conflict and the logical conflict. We can establish a link using the infinite distance here. So there's a means to establish some links between distances and conflict. And also another way to see some links is to say that the distance, the Euclidean distance between the plausibilities quantifies how much two functions are in conflict with the same set A. So if you compute the conflict of one mass function relatively to one set, difference between two, and you average, that's also a means to establish links between these two. There are probably other links that exist. But still, they capture different notions. They don't do, you can be, two mass function can be in conflict, while, no, I would say rather the other way around, two functions can be close to each other while being in conflict, for instance. So some ideas to combine the two aspects using a two-dimensional index. So this is one example, but it can be any other one. So a distance, and this is a way to quantify the discrepancy, let's say, between two mass functions, or using a product, for instance. So this is an inclusion index on all focal set for two mass function multiplied by a distance here. And it can be generalized. This is maybe a means to define other measures. And I'm not saying that we should do, but and what is important are really the properties. So I will just say some words about properties, mostly to highlight that this is critical to the definition of any measure. I didn't talk about the properties for the Unary measures, but there's a list of axioms, properties, requirements, depending on how you see them, desirable, whatever, but still, this is actually what gives you the semantics of what you would like to measure. So this is critical. And in particular, about properties of conflict and distance measures. So this is a list where they are all been put together for the both categories of measures. So some are very natural about bondness, the positivity, the extreme values that are natural, the symmetry that we generally would like to, but which is not required in some application, insensitive to refinement. So Thierry talked about what the refinement is. The monotonicity relatively to the imprecision. Here, this is an ordering based on the specialization matrix. So M1 is more specialized, is more precise than M2. Ignorance is bliss. Okay, I will come back later to this measure, so I won't detail. Reflexivity, separability, triangle equality, typically required for distances. So some of the properties are common to these two categories of measures, but here they are really the properties which distinguish the two categories of measures. So I will zoom a little bit on first the reflexivity properties, which means that the measure of M with itself is equal to 0. This is typically required for a distance measure. This is the intuition of a distance. The distance to you with yourself should be 0. But it's generally not satisfied by conflict measure. The conflict, for instance, the conflict of M with itself, as we show, is usually non-zero, because it allows to quantify some notion of internal conflict or internal inconsistency, as we said. The separability property, I say a few words at the beginning, earlier, which means that if the distance, or if the measure between two mass functions is 0, then necessarily the two mass functions are equal. This is not required for conflict measure, naturally, and it's satisfied only by full metric measures, so by full metric distances. So in the categories of distance, some are pseudometric. They don't satisfy this axiom of separability, meaning that you can get a null value while the two mass functions are different. What has been called ignorance is bliss by our colleague Sébastien Dempster-Shafer and Thomas Berger. M cannot be in conflict, cannot be more in conflict with total ignorance, the vacuous mass function, than its internal inconsistency. So, which is written that way, where phi is a measure of total inconsistency, and this is typically required for conflict measures and not required for distance measure. So, what to choose between conflict and distance? It's an open question, but still you can rely on the desirable properties that you would like for your measure, for your specific application, because they convey either a notion of conflict, a notion of distance. This is one way. You can play with the consistency degree between the different focal sets, the phi function, and also the meaning of the measure based on, for instance, the value of the parameter alpha in the Minkowski family, if you want to measure rather an angle, rather a distance versus a conflict. And in practice, if you have another optimization criterion that your measure is used only in your calculation, you use the measure that best satisfies this criteria. So this is for the meaning, and in practice, the best one is the one with your application. So I will conclude with some applications. So rather than, I try to group the applications based on what kind of notion the measure is quantifying. So more on the semantics than the more calculation and optimization aspect. So we can group information quality in general within two. Either it's the information of the quality of an information item, a unique one. So then we refer to, that is, if this information item is modeled by a belief function, we refer to the Unary definitions of specificity and consistency, a total ambiguity, if you remember Clause's typology, so consistency, specificity, which are the positive notion compared to non-specificity, discord. And binary, when you have two or more belief functions to compare, you can measure notions of correctness, credibility, or relevance. So I will just show you examples in practice, for instance, when it's interesting to measure correctness. So we can say naturally that a correctness assessment can be, so a mass function is correct in reference to a mass function representing the truth, whatever the truth is, or the reference, your targeted or reference function. So you know the truth, and then you can compute a distance or conflict measure to the true value that you are targeting. In general, M can be a categorical logical belief function focused on a singleton. So you know the true value, so it has a mass function of 1, and you want to compute the distance to this particular focal set. Or it can focus on another set, which is not necessarily a singleton. This is the example I will show you. So that means that your targeted mass function still contains some non-specificity. It's completely consistent because you know that it's this value, but you are still uncertain on some aspects. And it can be also any mass function that you decide is the true, it's the truth, and I will show you another example. So back to the problem of vessels in general. Now we don't want to know the destination. We don't mind where they go. We want to know who they are. So this is a problem of vessel recognition. We have a series of vessels. Splitted the list. The list is actually quite big, but I focus here on the most relevant vessels. We have 4 sources which provide evidence about the features of the vessels: speed, the length, all the different features, which are provide evidence about the type of the vessel. Actually, about the identity of the vessel. It's more the unique ID of the vessel. We have a sequential fusion process, each piece of information modeled by a belief function and combined with the previous one. So as long as when we receive evidences, when we receive reports for the different sources, they are combined with Dempster's rule. And this is the result of the correctness of the algorithm compared to different possible true value, possible targets. So we compute the distance to one specific mass function, which is this one in blue, which happens to be wrong, actually. The truth is really this one. And one of these three items, what we observe when we compute, here it's a Jacquard distance. When we compute the distance, we see that the algorithm, the fusion algorithm, converges toward this solution, which contains three elements. So we know that it cannot go further. And the fact that the set has more than one element, it's actually because the features, the sources don't have enough information to discriminate between these three things. So sometimes it's interesting also to know, to compute the distance to truth based on some subsets. Another example of mass function approximation, Frédéric presented yesterday some approximation algorithm. Here we use another one. So the idea is to keep the number of focal sets under control, because the more you combine with Dempster's rule, the more focal sets you create, and in the end you can end up with 2 power n focal set, which can be huge. So Prakash mentioned this, so you can define and you can remove all focal sets that have insignificant masses. In this case, we decide to keep, rather the other way around, the 8 most important focal sets. So we keep a number of focal set of 8, and what we would like to know, based on different approximation algorithm, we want to know which one provides the closest approximation to the original one, to the original mass function. So in this case, we see that the one algorithm, which is defined by Bauer, provide the closest approximation. So this is another example where the distance can be used to assess some notion of correctness when you have some run truth, whatever it is. Another notion now, which I called credibility, is actually referring to how much a given mass function is consistent within a group of other mass functions. So without access to ground truth. So you don't have any truth, it's rather you're within a group and you wonder how what you're saying is credible based on what the other said, assuming that, of course, they are providing independent pieces of knowledge, of course. This is another story, I won't talk about that. So the credibility can be assessed that way, where we reverse the notion of inconsistency in this case. So the higher the inconsistency, the lower its credibility. If you're the only one saying something, it's maybe less credible if you didn't speak with anybody. This is a credibility measure, for instance, but there are others, and I will show you another example, going back to the destinations of the vessel. So we still want to know where the vessels are going. We have the 4 sources providing information for or against the destination, of course, in terms of belief and the belief of the country. And when we combine this, we obtain, for 3 destinations here, we obtain these results. Here, we have the mass of the empty set, which is of course the same for everyone. We have the evidence for, which is the belief for each destination. The evidence against, which is the belief of the complement of the destination, so against this destination. And in between, we have the ignorance, which is the difference in between. So the question is, which source is provided in this context the more inconsistent information, where this value here, where this conflict is coming from. So we can use a measure of credibility derived from the consistency measure. For this example, we used Jaeger's measure. And it happens that, so this is the credibility that has been computed here. We can compute for the 4 sources that we had here. And we see that the information for the port capacity, so this is a database which tells you the size of the vessel. Depending on the size of the vessel, some vessel cannot enter in ports. So some ports are very small. So if you have a big vessel, you may not go in some specific port. So this source is maximally credible. And in this case, it's maximally credible because it's almost not informative at all. So it doesn't provide information. So of course, if you're not informative, you can be very credible because you don't say anything. And while the information from the maritime route, which provides an idea where the vessel is going based on the history of similar routes followed by vessel, is the one which is the least credible. So this is probably due to this source that the conflict arises here. So based on this, that kind of information can be used to refine the fusion process to discount possibly the information coming from this source. And this is interesting when you don't have access to meta information on reliability. When Frederick presented his talk yesterday, he referred a lot about the reliability of the source, which is a meta information you may have outside. If you don't have that meta information, you don't know what to do with the information you receive by the source. But you can still compute some notions based on the other information and refine the fusion process, discount information based on this value. Another example of credibility assessment for vehicle recognition here. The problem we had was possible misassociation, several vehicles, and it's possible that the information, so it refers to what Thierry discussed yesterday about associating the good information from one source to the same object. Otherwise, you are combining information which don't belong to the same object. So this is a critical problem. So anyway, I don't have much detail about this, but it's just an example to show you how non-credible pieces of information were discounted or discarded from the fusion process based on some notion of credibility. And here is the comparison of different measures of credibility on the final pygnistic probability. So we have 3 measures here, and we can see that depending on the credibility measure, so you have better measures, some measure of credibility are better to discount the corresponding mass functions. And I will finish with is a notion of relevance. So there are actually 2 aspects of relevance. So it's not what with when it's within a group, it's a particular mass function relatively to another one. And it's can characterize the impact of a piece of evidence on previous knowledge. So if it provides information, it's relevant. If it changes your state of knowledge, if it doesn't, it's irrelevant. Or relatively to another state of knowledge, in particular in problems of information retrieval or pattern matching. So this is just a definition. So we say, for instance, that it's relevant if the measure, conflict or distance between one mass function and what you had before, so after you combine, is different, is not 0. If it's 0 or very low, meaning that you don't have a lot of information, you don't gain a lot of information. In case of information retrieval, you can compute some retrieve relevant items. So if you have an evidential database where information is represented by belief functions, you can compute the distance and retrieve the most relevant. Or in case of pattern matching, you may want to retrieve just one. So this one is just a subset of it. Actually, it's not really relevant. So an example of relevant assessment for explaining complex model. Where we would like to know to quantify the impact of a specific piece of information on the final result. So the problem here, we have a problem of threat assessment. We have a series of sources. We know their reliability on a rough scale, and they provide pieces of evidence about a specific vessel. We have a classifier providing that it's a research vessel. We know the type of VIS. We know some kinematics, about the speed and its behavior. We have been able to identify that it's loitering and at some point that it stopped. We have some intelligence, which says that it's assumed friend, so it's a standard category of in the military domain. So there's, And then we have an analyzer, which tells if the IS is provided consistent information, it's not spoofed. That's basically, it's easy to change the IS values. So if you have inconsistency in the messages that are sent by IS, you can detect that it's likely spoofed. So we can project all these pieces of information in this space. This space is a two-dimensional space where here we have a notion of specificity, actually not a notion of specificity, but this art denotes a change in specificity, and here a change in consistency. So what we observe, for instance, so we see the global impact of each report on the final mass function. So we see, for instance, that the IS received doesn't say anything. So it didn't change anything. We can eventually remove it from the process. We see, however, that inconsistent IS information, so that the IS is inconsistent, increases the global inconsistency here, increasing the global inconsistency, and reduces the specificity. So it's less informative. So it reduces it. At the same time, this information reports increases the global inconsistency here, but increases also the specificity, meaning that it's more informational. So this information is actually one which is critical to the result. A final example of information retrieval when you have a problem with missing data. So you have a database of evidential items and you want to retrieve some items which are close to your query. So this was an example where the problem was a database with a lot of missing data. How do you, so there are some methods to fill in the missing field with data. Like some imputation methods. And we tried another method by replacing the missing data with different models. Either we replace with classical sets, so meaning we don't know what it is, but we put a subset, just a set, or we put a probability distribution, or we put a value function, and in this case, only simple support function because it was too big. We compute the retrieval and we can assess the quality of the information retrieval based on the F-score, simply, where we make varying the probability of missingness here. So the higher the probability of missingness, the higher the missing field, so the higher the missing data. And we compare the different models, the different way of representing uncertainty before the retrieval. And we can see, for instance, that the best model in this case was a simple support value function focused on a singleton. So, and it was better than the probabilistic model, which is this one. So that will conclude this talk. I will summarize. As I said, conclusion is a bad term because it's not really a conclusion, but rather a summary. I tried to show that the notion of consistency is at the heart of many measures of uncertainty that are both unary or binary. So we define the consistency between n sets instead of just the pairwise comparison, which is classical, both with the definition and the corresponding index. We defined that allowed to define the internal consistency of a mass function. We can see the consistency as a norm, which is the distance to the state of total inconsistency. And we can reverse the notion of consistency into a notion of inconsistency through a parametric function with A, allowing to put under the same umbrella, I would say, the minus log used in the entropy function. What is important to say about this function is that once you do this, you change the function, even if it's a continuous set of function. You change a lot because the logarithm guarantees the additivity of the measure. If you remove the logarithm using 1 minus, you lose this property. In some cases, it's not important. In other cases, it's very important. So again, it's really important to go back to the properties of the measures and not change parameters for changing parameters. By changing something, you change properties. About inconsistency. internal inconsistency of one belief function, there are two notions that are combined, of course. The way the masses are distributed over the focal set, which is one aspect, and also the way the focal sets interact. These two notions are captured in the internal measures of inconsistency. Some general formulation allow to reduce the choice of the measure to a small number of parameters, which do not include the criteria for selecting the measure. So n, the number of focal sets that you analyze and that you do with the intersection. The consistency, that can be just the intersection, non-empty, or an inclusion, which is a more restrictive notion of consistency, or equality, or even based on some quantitative notions. And as I said, the decreasing function. So again, be careful of changing these parameters. And we also define a monotonic family of measures of consistency. About external inconsistency, so families of conflict measures can be derived having as upper and lower bound existing measures. So it's refining and going a little bit deeper in the way conflict can be measured. Important to consider that distance and conflict measure different notions of discrepancy between belief functions. Conflict is defined as the inconsistency resulting from their conjunctive combination, so focusing on the empty set, while distance is defined as the consistency of their difference. So what is important is that here you focus on the intersection of the focal sets, here you focus on the difference between the masses. And some links still can be established between some conflict and distance measures, and there are other measures that are maybe interesting to explore, cross entropy, angle or divergences. Some have been already defined in the literature quite recently, but again, depend on the application and the purpose. So in practice, the choice of the measure should be guided by the semantics and the properties. So again, this is one of the most important pieces. We must distinguish between measures for Unary measures, we must distinguish between non-specificity measures, inconsistency measure, that was internal inconsistency, the topic of this talk, and also total uncertainty. Total uncertainty are assumed to capture both types of uncertainty. Binary measure allow to quantify some notion of quality, maybe others. I define 3 here, but it can be others. These criteria, or some of them, can be used to refine the fusion process. So I point to Frédéric's talk about that. And they can define some measures of performances used in information retrieval, in pattern matching, providing explanation, loss functions in classifiers, and here is several examples of distances or conflict measures that have been used in the computation of the clusters. So that concludes my talk, a series of references. So this work, especially on consistency, is mostly based on this paper with Frédéric and this one as well. So these 3 papers that you can see, the distance is here, and the measure work of Sébastien Desterck and Thomas Berger on the axiomatic of definition of conflict, which has been driven this presentation as well. Here, because it was mostly a survey, I will skip this. You have 2 slides of the definition of the measures that have been mentioned in this presentation, including here a quite new measure, as I mentioned, by Prakash and Rajim Zerosek, which has interesting properties. And finally, some references about applications. And that concludes my presentation. Sorry.